So looking a little bit back at our history, as you can see, this all started in the beginning of the 20th century, in fact, with an invention that was done by a scientist called Birkeland. He invented how to extract nitrogen from the air using a high voltage electrical discharge. And that was then used to compose nitric acid, which is a component heavily used in fertilizer. And that's also our core business, even still today, the production of fertilizer that is used in the agriculture industry. In 2000, well, that then led to the startup of a company called Norske Hydro, a Norwegian company. And in 2004, they divested Yara as a separate company, which is the company I'm working for today. Once that happened, we immediately started also next to producing fertilizer to look into more digital assets and how we could elevate our business by penetrating those markets. A little bit on our scale. So we have around 16,000 employees. Yara is a Norwegian company, but we also have a big satellite in Belgium, where a lot of the IT operations are done. We are selling our products in about 160 countries, and we had a revenue of close to $13 billion in 2019. We are a global company, so we have plants and offices around the globe. And more importantly, perhaps we reach over 200 million people with our products directly or indirectly every day. Also important to note, something we are very proud of, is that we were ranked among the top 10 companies in Fortune's Changing the World list. That is also something that I will come back to related to our mission. So our mission, responsibly feed the world and protect the planet, and our vision, a collaborative society, a world without hunger and a planet respected. Now, these are not just marketing slogans that we put on our wall, but this is actually reflected in everything that we do. We are a commercial company, so making sure that our shareholders are happy is one of our prime things to do. But even then, everything we do carries this mission and vision. Our digital agenda, as I explained initially, and that's still our core business, is to produce fertilizers, but we are more and more evolving into selling added value on top of that. That is mostly visible in what we call digital farming, where we equipped the farmers' machinery with all kinds of IoT sensors, so that when they go over their lands, we measure, for example, the compounds in the soil, like nitrogen, but also calcium, magnesium, to detect exactly what's underneath there. And based on all that information that we gather, combined with climate data, high resolution satellite images, we can then predict or make suggestions on what type of fertilizer they best use and in what volumes. That's all added value that we are selling on top of our products. Some example of these applications that we then built with that, as I explained, precision fertilization, and that's also a little bit reflecting our mission and vision, because instead of farmers just bulking a lot of fertilizer on their land, we now help them to tune that, and that's maybe a little bit contradicting the commercial sales of our fertilizer, because we are sometimes saying you should use less, but on top of that we are now selling intel information which the farmers can use to also have a better yield on their fields. So we even have also very precision, smaller scaled devices that we develop to measure the nitrogen in leaves of a plant, for example, to see how well or how bad they are doing. And then we have all kinds of other solutions also to optimize the utilization of water, for example, which is very important for our farmers in South Africa, to name one. So our strategic ambition is to really, instead of being a producer of fertilizer, is to become the crop nutrition company of the future. that is by developing those applications, helping our end consumers being more productive and driving innovative growth, both for ourselves but also for our clients. We see digital initiatives not only in our new digital farming initiatives, but also all over our company. In the complete value chain, more and more we see digital emerging. Next to digital farming, we also have our industrial solutions, where we sell side products that come from our fertilizer production, things like AdBlue that you might know that you add to your diesel engines, and also products used for example, in London to neutralize smell that is coming out of the sewer. In the past, we used to sell those products based on the demand. Now we are moving more and more into subscription-based models where we equipped the tanks of our clients with telemetry sensors so that we can better predict the amount of product they need to apply, and we can also measure when their tanks are going empty so that we can automatically also supply enough product just in time. Also in our factories, in our plants, more and more we are equipping our machinery with IoT sensors so that we can have use cases like predictive maintenance. Our plants always operate at full trust because we cannot produce enough based on the demand. So if we have an outage in a factory, that has a huge impact on our revenue. That is why also predictive maintenance is a very important case for us, being able to predict when a certain pump or anything will go down based on vibration patterns combined with climate information. So a lot of data that we use in those algorithms is also very important in our production. Now, how does that all relate to that journey we embarked on, as I explained, the API Economy program? We saw a lot of challenges, and I will highlight two of the most critical ones here. First one, integration. I think this slide is something that has been going on in the IT industry ever since I started, I think. Once we started to move away from the monolithic mainframe environments, we ended up with an integration challenge. This is now a modern version of the typical spaghetti slides that you might have seen before. Initially, we started to invent technologies to get beyond this challenge. For some of you that have been around for a longer time, you might have seen the emergence of the message bus, things like MQ series, where we would just plug that in and automatically this spaghetti integration would be solved. That didn't really happen. So then some smart guys thought maybe a message is not enough. Maybe we need to add a service on top of that. And then we had the enterprise service bus, which we then rolled in, and automatically the spaghetti would then transform into a nice layered lasagna. But also that didn't happen. And I think the main reason for that is because technology was not the problem. It's more the strategy behind. And that is also something when we started this API economy journey, one of the first things we did was to look at that strategy, define an enterprise-wide integration strategy, making sure that all integration solutions and requests were centralized so that we had a real one-stop shop for integrations within our enterprise, within Yara. Second challenge is, and this is a slide that you might have seen also at the Gartner event, but the bimodal IT, I think that is very typical for organizations like Yara. We are a big company, and we see this mode 1 and mode 2 complexity emerging. Mode 2, those are like our digital farming solutions, where those teams really need to be able to experiment, try something out. If it doesn't work, throw it away and try something new. If it does work, they need to get it out in production as soon as possible, because if they don't, somebody else will beat them to it. On the other side, mode 1, more our traditional corporate IT, and those systems like our ERP systems, CRM, They need to be predictable, they need to be stable, reliable, they just need to be there, and people need to be able to count on them. They don't need to change that often. They need to, as I said, they need to be stable. Bridging those two, because those newer digital systems, they heavily rely on the data that we have gathered over those years that we've been doing business. They are using that data to make those predictive models, for example. But our core backend systems are not really tuned for that high level of smaller transactions. If we sell directly to a farmer, digital intel, those are very small transactions where farmers can actually just pay with their credit card for certain information. Our backend systems are not geared for that level of transactions. Traditionally, we sell to our partners in a B2B model. Now we are moving in a B2C model. So making sure that we can cope for that, that's the bimodal IT challenge. And that is also something, one of the main reasons maybe why we introduced this API Economy program, to being able to cope with that. Now, talking about APIs, API Economy, maybe let's take a step back and explain a little bit what an API is. And I can hear some of you now think from, oh my God, is this guy going to give you a definition of an API in this community here? Well, unfortunately, yes, I am, because when we started with this, we detected that even within our own company, there was many different definitions of an API. And I'm sure even here, if I would ask you, give me your definition, I would get at least 5 different ones, and all of them would be true. And that's maybe one of the main problems with API. That's a term that's not new. It was there already in the 80s. I still have some books. Yeah, I'm that old indeed. Of that time where APIs are also referred to. So what is it, the API then for us in Yara? When I talk about API, I typically use the metaphor of a door. An API is exactly a door. It gives you access to certain information or certain logic, and it's nothing more or nothing less than a door. Just as with building doors in buildings, if you don't think about how you're going to design your door, you might end up with doors that nobody will ever use because they can't reach them or they don't find them. Also with APIs, designing them properly before you start thinking about how to build them is very important. And it's also something we stumbled upon a couple of times. So just like doors, APIs, they can give you access to something in a secure way. That's also why they need to have locks. They come in different shapes and sizes. You need to be able to tune that a little bit also depending on your consumers. They have an impact on people. If something doesn't work, it might have a big impact on your business. And they must be accessible and also discoverable. Linking all that then into an API economy, that economy is where we try to use the data that we have to augment our business, to monetize certain digital assets. And monetization might be directly by selling information, also might be indirectly by adding value to existing applications. When we started, one of the first things we did was to define this reference architecture, just to see what exactly do we need to set up this API economy, what do we have already, and where do we see gaps. An important thing when we define this architecture is the top here, the scalability. Because once you start exposing APIs within your ecosystem, all of a sudden you might detect that somebody from another ecosystem starts to use your APIs as well. And then scalability is completely uncontrollable. So you need to be able to cope with that. First thing we identified that we needed was this API exposure layer. So the green layers here, API management, API exposures, heavily linked to our security platforms. And then the blue layer is more the implementation of the APIs. So the green layers, those are the doors. The blue layers, that's what's behind those doors. Within our organization, we had a lot of integration middlewares. In fact, any integration middleware you can think about, we probably had it or still have it. That was a problem. We needed to harmonize that integration landscape. Next to that, we also introduced a microservices platform to build API implementations, and also because these days it looks like you can't go without microservices or you're not hip anymore. We did a big RFP for our API management platform, and MuleSoft Anypoint platform came out as best, so that is also what we are still using today. As I said, microservices versus integration services, that's became a little bit of a challenge, or a battle even, because you will always have those teams and people that say we can build everything with microservices. On the other hand, you have the more integration architects who rely typically more on integration middlewares. And this is also something that's been in the IT industry as long as I know. Now it's microservices. Before it was we can build everything in Java or in C. We don't need a service bus. So those are the typical things that go around. Within corporate IT, we try to define some algorithms or some patterns, some decision flows to decide on when to use what. And we detected it for integration and enterprise scale data exposure. Actually, application integration services were a better fit. We still have our microservices platform, and definitely when we build digital apps like in digital farming, those are heavily based on microservices. But for integration, we are more relying also on MuleSoft Anypoint platform, together with some other tactical solutions that we still need for our SAP environment, for example. Our journey, and I will not go into a lot of detail here, but we started in August 2018. We had our first use case going live in February the year after, which is rather quickly thinking about the scale of our environment. And then we had some technology challenges, moved a little bit within MuleSoft on their different products. And now we are running MuleSoft Runtime Fabric on top of our own Kubernetes clusters. A use case to look at, when one of the first ones we built was and I call it a tactical use case, because one of our business units, telemetry, were replicating customer data from one of our SAP backend systems. They had a lot of problems there because once they replicated that, they started to modify the data in their own system, so they had no replication path back anymore. We managed to convince them that replication of data was maybe not the best thing to do. So we built an API for them to give them real-time access to that customer data. And that really helped them a lot, because in the past they had some problems, for example, with shipping goods to customers where the address had changed. They didn't know about that, so they delivered the goods to the wrong address. That is now gone. They have real-time access. When I said that was a tactical API, when we built it, we already thought about the future because we knew customer data is something everybody needs. So both on the consumer side, we made sure that other consumers could also subscribe to that API, but also on the provider side, we have many systems containing customer data, and that is based on regions and different business units. So we also made sure that on the provider side, we could hook up more and more systems. For the consumer, that's completely transparent. So that's a sort of a context-based routing that we do here to make sure we give the right data back based on the request. Some numbers, we have today, I guess it's almost 60 APIs in production. We have about 15 million calls each day, or a month. But in fact, these numbers, they don't tell you anything. I've added this slide because I know some people like numbers, but the fact that you have 50 APIs or 10 APIs out there doesn't mean anything. It's the value that those APIs bring. This diagram here below shows how our APIs are integrating with other APIs. That's a real-time snapshot just that you can take from Anypoint platform. When we design APIs, we structure them according to our enterprise architecture domain model. That is really to disconnect our APIs from our organizational structure. That is important for naming conventions, but also for domain-oriented modeling. For each domain, we will typically define three main diagrams. First one is the information flow that shows how data is flowing between different systems. We have our application cooperation diagram where we describe the APIs on a three-layered model: experience API, process, and system API. And then we have our domain model or our canonical model. That's the vocabulary that we speak within our integration domain. So whenever we build a new API, the response reply structure, for example, the messages, they will be based on that domain model, so that the integration developers or the integration architects don't need to be bothered anymore by, do we call it a customer or an involved party or a client? No, that structure is defined and they can just reuse that. So this we build for each domain. Reusability, one of our main KPIs is in fact reusability. Every API that we build should be reusable out of the box. And that is something that doesn't come from technology. That starts with the design and the functional part of an API. That is why we also use that layer structure. And you can see that here, for example, that this system API is being reused by two experience APIs. And on the other side, you might also have system APIs, for example, exposing data from two different backend systems into the same process API. So reuse, again, doesn't start from the technical side. It also starts from the functional side. Reuse also, and I'll come to that here. When we expose our API, so we are using the Exchange portal also from MuleSoft. Obviously, that's also where reuse can happen. If people can discover an API, they can subscribe to it using that portal, then they can also start to reuse that. This is something we are still trying to find the best fit way for our environment. It's not an easy task because you can have a lot of assets out there, but not everything is as reusable to your business stakeholders, and making that understandable for them is a challenge. We have an internal portal and we also have an external one where we can publish our public APIs. So to summarize, the API economy helped us to realize that bimodal IT, it promotes reusability, makes our APIs and our data visible in a secure way, and it allows our business units to monetize on our key assets, our information, and our data. Again, to stress, define the strategy and the sponsorship first. So before you start thinking about how you're going to do this, think about what you want to do. Also select the right technology and the right partners. We heavily rely on MuleSoft for their technology, along with some other technologies that you can see here. And we partnered with Capgemini for the infrastructure and API delivery, and also with AE for the architecture, design, and the also delivery. Our delivery model, we are still learning there a little bit, but also greatly with the help from AE, we are now finding a good fit for our API economy, which is we are working Scrum based. We have utilized the team topologies to help us define the right structure. We are now landing on a centralized governance with regional satellites, and we are structuring our delivery teams according to our domains, more or less. And that is still an ongoing journey where we are improving as we go. Then some lessons learned to conclude. Change management, API economy, it's a community. And I think everything related to APIs is in fact a community. It's sort of an open source model where everybody can contribute. So think about your stakeholders. Who exactly are you trying to reach with that API economy program? get them involved as soon as possible, because otherwise you will most likely fail. Strategy, I just explained on a previous slide. Think about a strategy before you start thinking about technology. So what do you want to do? And then think about how. Funding and delivery, we have a centrally funded model, but in the end, we want our consumers to pay for the added value that they get from using our APIs. So internally also, our business units will start to fund their own APIs. APIs and integrations, I think that's an ongoing struggle. Not every integration needs to be an API. And that is something I've seen many people fail with by making everything an API. API first doesn't mean everything is an API. And then, yeah, something very typical for larger organizations that are using SAP backends, have a look at your license model, because sometimes your traditional license model might not allow you to open up your backend system using APIs. Well, you will be able to do it, but your vendor will be coming with a big bill for that in the end, if your license model isn't tuned for it. Okay, so that was, I know I went through it rather fast because I only had 20 minutes, but I hope it was of value to some of you. So thanks for listening. And if there
Thanks
are
for the interesting presentation, Stefan.
You're welcome.
We already have a first question from the audience. So basically, Jonas has questions on the monetization of your external APIs. So he wonders if you could describe the pricing models of your external APIs.
No, I can't, to be honest. The main reason is so the external APIs, mainly in our digital farming units, we started off by giving them for free, just to experiment also and get them scaled to the right size. But in the end, it's going to be depending on the size of the end users. We will have different subscription models with different tiers. So you can have a gold subscription where you can call that API as much as you want. But we can also have like silver or bronze subscription where you pay less and you can use that API, for example, 10 times a day. So those are more or less the models we are going into.
And then another question from Jonas was, what are the decision criteria you apply at Yara to go for an API integration or not?
To go for an API integration or not. We do use the API first paradigm. So we will first look at, do we already have an API that exposes the data that we need to integrate? If yes, then we will start using that. But the challenge most often comes, look at your integration request. Sometimes it's more about ETL type of integrations where you don't typically want to use API. So I think the volume of the data that you're trying to integrate will mostly predict whether or not an API is suitable. For me, APIs are more about real-time data requests and not so much about bulking data between two systems. But that is the more or less a directive I use for that.
Yeah, makes sense, in my opinion. I see that at the moment there are no other questions from the audience. I propose to give the word to Alexander and to move ahead. For people in the audience, if you still would have questions for Stefan, you can still put them in the chat and then we can tackle them also during the second Q&A or afterwards in written. Okay, Alexander, the floor is yours.
Okay, so hi, I'm Alex. I'll be talking about operational follow-up of APIs today, or at least my take on the matter. So let's start with a quick introduction. I work for Cubitec and we build custom enterprise solutions using our own platform. We specialize in integration and web application development, and I'm the technical lead within Cubitec. So I want to talk to you about a project I'm still working on for a customer. which highlights our need for the follow-up. You probably know Bevat from its battery collection business. Basically, in most stores and schools and stuff like that, there will be a barrel where you can put your used batteries so they get recycled. And about a year ago, they wanted to evolve their business, mainly by adding IoT to the devices, so they can measure things like fill level, temperature, and things like that. And they also wanted to restructure internal IT, for example, get rid of manual processes where possible, get rid of point-to-point connections and things like that. We have a dual role in this story because we are both the integration partner and a web application partner. Now, the web applications are in general slightly less relevant to this crowd, except for the fact that we do build single page applications, which means we use APIs to talk with our own backend. And so while we have different design guidelines, obviously for both of these domains, they do share a lot of DNA. So let's look at what's been built so far. We have two API layers, so basically the integration part and the web application part. We've built a number of web applications which are not really relevant right now. Then we have some standard integrations like a warehouse management system, Azure, geolocation, things like that. We have a pretty deep integration with their custom ERP. And then we have some third parties that have been integrated to provide certain informations. For example, if that barrel in the store is full, it has to get picked up. It has to be delivered to a sorting partner. And from there, it will move on to other partners until at some point it comes back into probably another store. And they want to keep track of every step along the way. And then the one we're currently working on is the integration with the battery sorting. So basically, once the barrel arrives at the battery sorting, they just put it on a conveyor, and then they start sorting it according to type and things like that. And we obviously want to keep informed if there are things that are wrong, for example, the wrong type of battery or whatever. And they need feedback on what is this barrel, where does it come from, and things like that. And then we obviously have an integration with the IoT partner that sends all the data from the devices, all the sensor data, and we can also send data to the devices like configuration and stuff. And then we have an API for customers where they can access their own data. So basically, as you can see, a lot of these integrations go in both directions where we expose APIs and consume APIs. Now, in a perfect world, we would build this, we would put it in production, and well, it would just work, and there never would be any problems. But obviously, that's not the reality. Things will start to fail, and that's kind of the point of the operational follow-up, as I see it, is basically making sure that everything keeps running no matter what happens. And I see three challenges in that. The first is prevention. So basically, even if your system is doing fine, you want to keep on top of, for example, performance bottlenecks or abnormal behavior in some way before it spins out of control. Then we have the expected issues, the expected problems, where you know something will go wrong at some point, but you cannot prevent it. You can only prepare. For example, there are some business things that we know, like the devices will get damaged. They will not be able to connect to cell towers from time to time. And on the technical side, for example, our third parties might have maintenance windows during which they won't be available, and we have to be able to cope with that. And then obviously the meat of the story, the challenge really is the unexpected problem. So dealing with things you did not predict. And I have some examples of that as well. For example, we had binary data suddenly arriving at our APIs because there was a firmware mismatch in the devices. We've had API calls fail because a few months prior to that, a CSV upload was missing a few lines. And things like that really, they ask a lot because you need to find the answer, obviously, to that problem, whatever it is. And so the challenge there is at some point in time in the future, you will have to figure out what went wrong. But currently, you do not know what the question will be at that point. Something will go wrong. You don't know what. And that's pretty hard to do, obviously. So how do we do that? If you have a real-time and historical overview of any significant event that occurs in a running system, you should theoretically at least be able to answer any question. And that's kind of the goal. The problem here is the word significant, which is usually a hindsight evaluation. So it's usually only after the fact that you know how significant something is, which leads you to generally over-capture data. So capture more data than you actually need. And you have to be careful there because it's a balance with capturing way too much data. It's very easy to generate a lot of data that's never relevant. So some examples of what can be potentially interesting is exceptions being thrown, obviously, is the prime suspect of something that goes wrong, especially the unforeseen ones. Then validation problems, security violation, rate limits being hit, API calls as they enter the system or as they exit the system to go somewhere else, resource shortages, cache misses. Sometimes you just want to log the raw HTTP request response data for later inspection. There are a ton of potentially interesting events depending on whatever question you want to answer. So I divide this into 4 separate steps. We have the collection phase where we try to collect all the data. Then we have the notification phase because we don't want to be looking at a dashboard all day long to get any conclusions. We want to be proactively notified when something goes wrong. Then we have the interpretation. So we have a lot of data that we captured. How can we find the answer within that data set? And then lastly, action. What can we do at this point? Either we can solve the issue or we can mitigate it in some way until the fix is actually there. So let's focus on collection first. In a traditional scenario, what often happens is you have a server which is writing information into a log, just a plain text file. And then you have another server doing the same, another server doing the same, and this goes on. And then you just take all these log files and push them into an elk stack. And at that point, you hope that the considerable search capabilities of Elastic will allow you to find the answer that you're looking for when it's needed. But there are some problems with this approach. Log files are by definition unstructured. You can try to add structure to it, but it tends to be hard, especially cross-system. In most cases, these are separate narratives. So basically every server is logging its own interesting tidbits, but most actual problems, the most interesting problems, will require logs from multiple servers or multiple systems that are involved. It's generally not the full story. So basically we're taking the server logs for microservices or whatever setup you have, but there are probably other logs that might be interesting to you to get the full picture. Like if you have a separate API manager, it might be logging stuff in its own database, which might be relevant to your investigation or not. It can be hard to change this particular setup because what often happens is developers at some point have to implement the actual logging. So if at some point you have an insight and you say, we should add something to the logging to make it more clear, it probably requires a deployment cycle. And lastly, I do want to mention GDPR because in this scenario, we are pushing a lot of data into an unstructured format. That data often contains some form of personal identifiable data. And then we're just copying it all over the place, which makes it harder to clean up afterwards. So we used to do this as well, looking at the server logs mainly for answers. But over the past few years, we've been switching to a new system where we basically have a continuous stream of significant events. And each block on the line at the bottom is basically an event in a fixed structure. There are about 60 fields in it with relevant metadata. A lot of that metadata is automatically filled in depending on the context. You can obviously add custom data and stuff like that. But the main clues, every event has the same structure at that point. Then we started retrofitting every part of our system to start emitting events into that stream. So, for example, our proxy might emit an event when it cannot match an incoming request to an actual HTTP server. Our HTTP server might log the raw request response data, or it might log some violation in the headers or whatever is relevant. The API manager might be logging rate limits. Rate limits are being hit. It might just log all the access incoming and outgoing. Business logic is obviously the most common location of the stack traces, so this is very important to follow up as well. Then the web applications, I do mention them again here because the analytics in our web applications can be added into this event stream. So every button that the user clicks, every page visit, whatever it is, can be added into the event stream to augment the contextual information you have at the point that you want to research. And then obviously all the other systems that we use every day to solve the problems of our clients, like workflows, scheduler, and things like that, they've all been retrofitted to emit events that they deem is necessary for logging purposes. Final source of events, which is interesting from time to time, is from metrics. So we keep a continuous metric data about most things that the server is doing, like how long does every query take to the database, how long does it take to get a free connection to the database, how long does it take to stream a response back to the client. And we add to that information about CPU load, heap usage, non-heap usage. So you have a lot of data being pushed into metrics. and then you can add rules to that to detect, for example, a sustained threshold. So if at some point one of these metrics becomes problematic, we can send events and again add context into the event stream. Once we have all that data, that standardized stream, we obviously have to store it somewhere. So we can push it to our cloud solution where we can simply review all the events. We also have a local solution where we push it to a database on site with the same tooling as the cloud tooling. We can still push it to Elk, obviously, and we can also push it to a server log. At that point, we will, by default, anonymize the data, and we use the common event format for serialization. So now that we've collected all the data, let's have a look at notification. So one of the key parts for me for notification, also partly interpretation, is the classification process. The clue is events almost always contain a lot of data, but they don't always contain the conclusion. And a clear example of this that we probably all know is a stack trace. So basically you have a long piece of text, and somewhere in there, based on some keywords, there is a conclusion to the stack trace, what it was. And I've seen teams in large companies in production, for support reasons, simply have a long list, sometimes even in Word, which just said, if you see this and this keyword, then it's probably this kind of thing, and you should be doing whatever it is. I've seen horrible queries in Elk trying to do something like that as well. But the thing is, often if you look at this event and you don't have the query at hand or whatever, you might not know what it is and you have to manually scan it again. So we push it through a rule system where it can be tagged as being something specific. Like in this case, we know it's a cell tower unknown problem. And then the next time when I look at the stack trace, I don't have to do the manual mental labor of interpreting. I can just look at the conclusion. And also because we store the conclusion, we can also draw metrics from that. At some point in the future, we can do reporting on this particular type of event or in conjunction with other events. And a second part of classification is priority. So by default, all the events have a priority 0, and anything between 0 and 500 is considered to be informational. So it's generally either for the prevention part, so monitoring, or for the contextualization part, so adding context to other events that might be relevant at some point. We use ranges, so you can per project add your own levels while still being able to draw some generic conclusions. Anything between 500 and 1,000 is means basically the next time you're in the office, you should definitely have a look, but it's not mission critical. Anything above 1,000 is drop whatever you're doing and focus on this now. We have a severe problem. And then depending on the priority and whatever you have, we can send a signal to our signal framework, which is basically a tree of rules, so business rules. And we can check, for example, it's a signal that comes from the event framework. We can check it's a medium priority in this case. We can check the classification. It's a cell tower unknown we classified before. And then we can conclude that we should send a mail to Bob because Bob can somehow fix this. The thing is, when you do signaling like this, so we're sending mails to Bob based on events, you do have to be careful for what I call the error storm, which is probably something we've all saw happening. Basically, you have a critical piece of infrastructure like a database, which is running just fine until at some point it isn't. You do not get a single event saying, oh, the database is down. Oh, no. You get a lot of events saying that the database is down. And if you're not careful, Bob will be getting a lot of notifications. So we added the concept of a trigger interval to the signal framework where each rule can be triggered only once within a particular interval. Now, we did add additional concept called trigger context, which allows us to differentiate a little bit. For example, in this particular example, let's assume we put the trigger key to the server. So the server name or ID, whatever you want to call it. That means if server 1 can no longer connect to the database, we get one notification. And if within that trigger interval, we get a second server that can no longer connect to the database, we still get a second notification. So the contextualization allows for repeats if necessary. So now that we've been notified that there is, in fact, a problem, we want to be able to interpret the data. And for me, this is the most important part, because if you have an event, it's like the last page in a good book. If you skipped all the other pages to get to that page, you do not really know what it's about. And the same with events. Events have a lot of data. They're very interesting, but it's usually a lot more interesting to get all the events that occurred before it, because the event itself is often a cascade from one or more things that happened before it. So how can we do that? Every event that is created within a single execution unit is automatically correlated to each other with the correlation ID. One API call is, for example, a single execution unit. So if you have any event within that API call, you can immediately check all the other events within that API call to form the context. We can go even further because the correlation ID can be passed in through the HTTP headers of our API call, for example, and it can be passed along when we call other systems to perform something. That means the correlation ID can be cross-system, allowing us to get events not only from one server, but multiple servers, depending on the situation. I have a tiny example here. So basically, suppose this is an incoming call we had from the track and trace. It failed. Okay, that's good to know. But we want to know why, obviously. It's a pretty complex call if you look at the business logic. We can immediately check what the correlated events are. Now, this is a flat list of events, which is not always the best way to interpret the data. But because there's so much data, there's often different views that are relevant depending on the question you're trying to answer. One that's particularly relevant is the tree view, where you simply have a different look at the same data, but here you can immediately see the narrative. So how did it unfold? How did we get to that situation? And we can immediately zoom in on the actual problematic call that was being made. Because in this case, we had the HTTP logging turned on, we can drill down. We can see the original HTTP request that went wrong, so the one that triggered our interest. And then we can immediately switch to the actual call we did to the ERP that caused the original problem. So finding the root cause, even in a complex interaction between systems, becomes trivial. But correlation does not have to stop at events, because once you have the concept of a global correlation ID that everyone knows about, you can start passing it along. So we pass it along to our workflows. They know the correlation ID to batch jobs, scheduled service, whatever you need there. And we also know it from an auditing perspective. And auditing is interesting because it allows very flexible insights into runtime. So basically, you can have a flexible insight into the state of any running system and start logging whatever else you might be interested in at that point. And it can be linked to our automated database change tracking, so we can track what actually got inserted, updated, deleted in the database within that context. So by having this correlation ID linked to a lot of other different systems, we can get a full story on what happened. And depending again on what you want to know, can be interesting or not. But if you have all this data being captured, you can obviously draw more conclusions from it than only problem solving. For example, and this will depend entirely on what you're building, you can measure HTTP calls per hour or whatever time frame is relevant. You can be more specific and ask HTTP calls per user per endpoint. You can check what calls we're doing to a remote system, how many and whatever. We can check average response times of any of these. We can check geographical distribution of our users, amount of page hits in a web application. We can check funnels where we identify sequences of events that for whatever reason are interesting if they happen in that sequence. There's a ton of insights you can get once you have this data stream up and running. And the last bit I do want to talk about is action, but it's a very short bit. So basically, once you know what the problem is, you obviously want to do something with that information. And we generally provide 2 additional applications to all of our clients. The first one is a business follow-up, because we love empowering the client to solve their own issues when possible. So this basically focuses on expected problems where we know beforehand this will happen. We give them only the data that they really need to make an informed decision. We give them only the actions that are relevant within the context. And so they can do some basic error resolving at that point. They can also tweak the business configuration, like if there's a mapping table which is missing an entry because it's a new one or whatever, they can easily do that within this portal. A second portal that we always ship is the technical follow-up, which is usually the one we use, obviously. And it's aimed at the prevention part and the unexpected problems. So basically here you get all the data, everything you have, you get all the actions that are possible, and you have to make a good decision on what should be done. And also you can tweak the technical configuration at this point. So you can disable queues, you can set up schedulers, you can retry workflows if that is relevant to your problem. Obviously in this part, our web skills are very relevant because the business follow-up especially is usually a very custom application. And the technical follow-up is generally, we have templates, we start from there, and then we tweak if and when necessary. So I think I might have gone through that a bit fast. I have no idea on the timing, but are there any questions?
Thanks for the presentation, Alexander. We have a first question from Peter, who has some questions on the observability tooling that you're using. He wonders if it's built on open standards and APIs, such as OpenTelemetry, or if it's a proprietary technology or invention from your side.
I was definitely inspired by OpenTelemetry and things like Dynatrace, but in the end, it is currently a custom solution.
I will maybe from my side pose a bit further. What was the reason that you did not decide to just adapt such an open standard?
We have a, I would say, unique stack with some capabilities. And this was a more flexible approach, I would say, to build this. Gave us more control and more things we could do. Because we started out with Dynatrace, I was actually the first one, and I built an API that was agnostic from Dynatrace, and which obviously matches pretty good with what you could do with OpenTelemetry, but it was too limiting for what we wanted to do at that point.